Bismillah ar-Rahman ar-Rahim. Uh, in this video, we will do a fluid mechanics problem, chapter 2, section 2.8. We will be talking about hydrostatic fluid forces acting on a plane surface. With these plane surface could be vertical, could be slanted in an angle, and these are the type of problems that we'll be solving in this video from this book, this edition, and this is the book information. All right, so the problems that we will do, as we mentioned, will be from section 2.8, page 84. The first problem is 2.54. So the first thing that we have to do is to read the problem and make sure that we understand it. It tells us a circular 2-meter diameter gate is located on the sloping side of a swimming pool. The side of the pool is oriented 60 degrees relative to the horizontal bottom, and the center of the gate is located 3 meters below the water surface. Determine the magnitude of the water force acting on the gate and the point through which it acts. The next step, what we should do, and it's highly recommended in these types of problems, is to sketch or to draw what you have so you can have a better visualization of what is given and what need to be found. So in this problem we are told that we are dealing with a swimming pool, and we have a gate. The gate shape is circular with a dimension of 2 meters, and this gate is located on a sloping side, so slanted side. So let's draw a slanted side. So this is our gate. This is the slanted side in here. Slant means slope or lean. It's not vertical or horizontal distant. So so this is ours in here. This is called the horizontal bottom. So this the side, which referring to the sloping side of the pole, is oriented 60 degree relative to the horizontal. So this is our 60 degree right here. It tells us that from the water surface, below the water surface, the center of the gate is located 3 meters. So this is the water surface. In this swimming pool, the type of liquid that we're dealing with is water. And the distance from the water surface to the center of the gate is 3 meters. So, and this distance right here from we call y sub c. Y sub c is this is the definition of y sub c. It is slant distant from liquid surface, in this case the water surface, represented by this dashed line, to the centroid of area, to the centroid of the circular gate. So that's the definition of y sub c. Now, this water, we want here what we are asked. We are asked to find the magnitude of the water force. So this is called the hydrostatic force acting on the gate, which will be this one. We call it the resultant net force. And the resultant net force is usually act a little bit below the centroid of the gate, or the centroid of the shape that we are dealing with, whether it's circular or rectangular. And we call this point the center of pressure. And this distance we call it y sub r. And y sub r means what? This is the slanted distance from the liquid surface to the center of pressure. So that is the distance where the resultant force due to the water weight acting on the gate. That's where this resultant force will be located. And this resultant force is usually located below the centroid of the gate. So here to visualize further the problem, as you can see here, we are dealing with two triangles. So let's draw the water surface in here. All right. And let's draw the slanted distance from the liquid surface all the way to the center of to the centroid. And the distance from the centroid all the way to the top, this 3 meter. This 3 meter, we call it h sub c, height, h sub c. H sub c, just from from looking at this triangle, it's the distance from the liquid surface, in this case water, all the way to the centroid. And this is a 90-degree angle. So the question, what is the angle right here? As you can see in here, this horizontal bottom with the slanted sloping side, and then the water surface, it resembles the shape, the Z shape. So and from geometry, we know that the interior angle, 60 degree in here, will be the same angle in here. So that means this angle right here will be 60 degree. And, we can, utilize the sine and cosine to find, for example, y sub c. So, for example, sine 60 degree, sine is what? Is opposite, and the opposite is h sub c, divided by hypotenuse, which is opposite to the 90-degree angle, which is y sub c. So in here we have the angle, we have the height from the water surface to the centroid. We don't have y sub c. So for example, we can use this expression to find y sub c. The next triangle is, let's draw again this water surface line, and let's draw now the y sub r, which is the slanted distance from the water surface to the center pressure, where the resultant force will be located. And let's draw a vertical distance, and we will call this hc sub b. So from the shape, it's from the water surface all the way, instead of the centroid of the gate, that's to the center of pressure, or where the resultant force due to the water on the gate will be located. Again, this will be 90 degree, this will be 60 degree, and we can utilize the sine and cosine equations to help us find missing lengths in here. All right. So again, what is our goal in here? The two main things that we want to find, and this problem is asking us to find, is it tells us what is the magnitude of the force due to the water acting on this gate, and where is this force located? So how much will this resultant force be below the centroid of the gate? So these are the two questions that we need to answer in this problem. So let's see what we have to do here now. So now we want to find F sub r. Now, we know that pressure is force over area, correct? Yes. So here what we will do is we will solve for the resultant force. So now let's solve this problem. So we will take area, take to the other side of the equation, so it will be pressure times area. And we know that pressure is what? In this case, we are dealing with hydrostatic forces, fluid forces. This expression, we know it as the specific weight of the fluid times the height. And as we increase in depth, the pressure increase. And that's what we're going to do in here. So the resultant net force will equal to the specific weight of the liquid, in this case water, times the depth h sub c times the area. And this, we call it the hydrostatic force on a plane surface. Next, let's plug in the values. So the specific weight, we know that it is rho times g, density times gravitational force. And the density of water is known to be 1,000 kilogram per meter cube times 9.8 will give you 9810 Newton over meter cube. H sub c is given to us in the problem statement, 3 meter, and that's what we have in here. The area, and it tells us in the problem statement that we're dealing with a circular gate. So the area of a circle is pi over 4 times diameter squared. So 2 squared will give you 4. The 4 will cancel with the 4, so the area will be pi in this case. So when you plug this into your calculator, it will give you the resultant net force, that's the magnitude, is 92457.1 Newton. That's how much force will be applied from the water on the gate. So the next thing what we want to find is y sub r. Now, I don't want, you can look at fluid mechanics problems and you can go over how you can derive this problem. This is the equation that you use to find to locate the hydrostatic force acting on a plane surface. So let's think about it. What is y sub c? We want to find what's y sub c, right? That's why it's important to recognize these two triangles in these types of problems, because it will help you and aid you find such missing values. So in this case, y sub c, we can find it from this expression. So y sub c will be 3 meter over sine 60. So y sub c will be 3.46 meter. So we found y sub c. What do we need else? Area. Area, we already know what's area. 2 squared, 4 cancelled 4, so area will be pi. So pi area, we have it. So what is I x sub c? The I x sub c is the moment of inertia about x-axis through the center. So we want to find here what is this value. So now you can go to any engineering statics or even I think in the fluid mechanics book, you will find tables for different or common used shape, like a circle shape, where it gives you the area, the centroid, and the moment of inertia at different axes, and it looks like this. So it will give you a figure, area and centroid, area, moment of inertia. So in this problem, what we're looking for is this: I x sub c equal to pi a to the power 4 divided by 4. A in here is this a, so which means radius. Now if you think about it, what is the radius of 2 meters? 1, right? So this one will be pi over 4. So I x sub c will be pi over 4. So let's rewrite this and plug in the values that we found. So y sub c is 3.46 meter plus, this will be pi over 4 meter to the power 4 divided by the y sub c, again we found it to be 3.46, times the area, which we found to be pi. So we plug this into our calculator, and y sub r is 3.54 meter. So this is the distance this is the slanted distance from the water surface all the way to the center of pressure, right here. So this is y sub r. And obviously, if you want to know how much the resultant force offset below the centroid, you can find this distance by subtracting y sub r minus y sub c. Next problem, 2.55. In this problem, we are told that we have a vertical rectangular gate is 8 feet wide and 10 feet long and weighs 6,000 pound force. The gate slides in vertical slots in the side of a reservoir containing water. The coefficient of friction between the slots and the gate is 0.03. Determine the minimum vertical force required to lift the gate when the water level is 4 feet above the top edge of the gate. So when you have such a problem, as we mentioned in the previous problem, sketch it. So let's sketch this problem. So here, what are we dealing with? It tells us that we're dealing with a reservoir. So let's draw it. So this is the bottom of the reservoir, and these are the slots. And inside the slot, we have the gate. And we continue with the reservoir going up 4 feet, and this will be your water surface. And this reservoir, the type of liquid is water. So we are told informations about the rectangular gate. One, it is a rectangle, which is 8 feet by 10 feet. So let's draw it. So this is our rectangle. That's if you look at it from this side. So it will be 10 feet long and 8 feet wide. Now, when this gate goes up and down, when it goes up, it will have friction with the slot. So that friction coefficient is given to us as 0.03. And we are given that the weight of the gate is 6,000 pound force. So now let's take a closer look at this gate. So this gate obviously will have a force, will have a hydrostatic force due to the weight of the water, correct? And as we mentioned, this hydrostatic force acts at the to find the resultant force, it acts at the centroid of the gate. So this will be your force resultant. What other forces will be applied on this gate? We have the weight, 6,000. That's the weight of the gate. What else? The force that we need to find. We want to lift this gate, the vertical force. So let's call it force lift. And that's what we're looking for. And as we are lifting the gate up, the friction force opposes the motion, so it will be down. So that's the force of friction. Now this gate is in contact with the slot surface. So from Newton's third law of motion, the resultant net force, the hydrostatic force due to the water weight, acts normal to the gate. Obviously, the slot wall will also act in an opposite but equal direction force. So that will be your normal force. So this resembles what? An engineering static problem where we sum the forces in the x, in the y, and we sum the moments to help us find the different forces that we need to find. So here, let's sum the forces in the x direction. Let's say going to the right is positive and going to the left is negative. So F sub r, go to the positive, F sub n, go to the left, negative. So now we can solve F sub r which is what we mentioned, Newton's second law. Now, the sum of the forces in the y direction will be the lift force going up and the weight and the friction force going down. And that's what we have in here, equal to 0. And our goal in here is to find the lift force. So force lift will equal to the weight of the gate plus the friction force. So from engineering static, friction force is what? Is the coefficient of friction times the normal force. And the normal force is equal to the hydrostatic force. So mu times F sub r. So what is F sub r? From the previous slide, as we mentioned, it's the specific weight of the water times h sub c, and again, h sub c is the vertical distance from the water surface all the way to the centroid times the area. So the area in here, we can find it in here. This is a rectangle, so 10 by 8 will give you 80 feet squared. Next, h sub c, so we know that this is, so half of 10 is 5. So when we go up 5 plus 4 will give us what? 9. So that will be our h sub c. That will be 9 feet. Now the specific weight of water it will be 62.43. This is something that you can find in property tables, and then we're gonna plug in the values that we found and with the values that were given, and it will give us the magnitude of the force resultant is what? 44,949.6 pound force. So now when we found the hydrostatic force, what we will do is we will go back to the lift force to find what it is. So the weight is 6,000 pound force, and mu is given to us as 0.03, and the hydrostatic force acting on a plane surface, we found it to be 44,949.6 pound force. So that will give us that the lift force is 7,348.5 pound force. So this is the required force to lift the gate. All right, next problem. This problem 2.56, it tells us a horizontal 2-meter diameter conduit is half filled with a liquid. This liquid specific gravity is 1.6 and is capped at both ends with plain vertical surfaces. The air pressure in the conduit above the liquid surface is 200 kilopascal. Determine the resultant force of the fluid acting on one end caps and locate this force relative to the bottom of the conduit. All right, so what do we need to do in here? Sketch the problem. So this is our conduit. Great. And this is a 2-meter diameter circular conduit. Half of the conduit is filled with a liquid. And this liquid specific gravity is 1.6. Now, above the surface of the liquid, what do we have? The problem told us that we have air. The pressure of the air is given to us as 200 kilopascal. And remember, this conduit is 2-meter diameter conduit. Now let's take a look at the side view. So imagine that you're looking at the conduit from this side, and that's what we're going to have in here. And this will be our cap. Now here's a very important thing. When the cap, before the important thing, the cap, what does it do? it prevents the fluid, in this case the air and the liquid, from exiting the conduit. So in this problem, the goal is to find the resultant force due to the liquid, in this case air and the liquid, acting on the cap. Now, in this conduit, we have air pressure. Whenever you have air present, and this air is pressurized, according to Pascal's law, the pressure acting on a static fluid surface, just like what we have in here, this is a static fluid surface. The air pressurized get transmitted equally in all directions. That is why the pressure will act on the entire surface of the cap, and that's what it will look like. Now let's take a look at the liquid. The liquid, as we said, is half filled, and as we know, because this is a liquid, because this type of fluid is incompressible, as we increase in depth, we increase in pressure, correct? And that's what we're gonna have, and it resembles the rectangular shape. So our goal is to find the resultant force from the air and the liquid on the cap. And our goal is to find the force resultant net. And in this problem, we also are asked to find locate the force relative to the bottom of the conduit. So this is the bottom of the conduit, and we want to find this distance y. Okay, so before we move on, as we mentioned before, and we did in previous problems, we used whenever we find the magnitude of resultant forces, we need to locate. Sorry, whenever we find the magnitude of the hydrostatic forces, the next step we usually do is find and locate where these hydrostatic forces act. And to do so, the equation requires the area of the shape and requires the area moment of inertia. So before we proceed, let's take a look at the shape or the shapes that we are dealing with, and let's pull up from the reference table these shapes and know what are we dealing with and what are the equations that we're going to use. So for example, the air, as we mentioned, will act on the entire cap. And what is the shape of the cap? Is a full circle. And that's what we have in here. And as you can see, this one acts in the y, this is the y direction, just like this one here, the y direction. So that means that the center of this, the centroid will be in A, which is the radius. So if this is 2 meters, so it will act 1 meter below or 1 meter up. All right. And let's say this is the resultant force due to air. Next is this. Now the liquid acts only on the bottom half of the cap. And the bottom half is a semicircle. So this line right here where the x-axis is the water surface, and we need to find the distance to the centroid. So y sub c will be this one right here. And that will be the liquid force. This is the resultant force due to the liquid acting on the cap. So now we defined where the centroid is. And when when we find the magnitude of this resultant force and this resultant force, we add them to find the net resultant force. Great. So now we found the magnitude. Now, how can we find the location? Now, we can utilize, using moments to find the distance, because what's moment? Moment is force times the perpendicular distance to the axis of rotation. So let's take the axis of rotation at the bottom, because we want to find the force relative to the bottom of the conduit in these cases. Now, if we want to take the moment in here, what will we have? So the moment is the force of the area times from the centroid to the axis of rotation, that will be r, the radius, plus the liquid force will be from the centroid to the axis of rotation, the perpendicular distance. And to find that, so from the water surface all the way to the axis of rotation is 1 meter. And from the water surface all the way to the centroid will be this expression, 4r divided by 3 pi. So to find this, you will subtract 1 from y sub c. So 1 minus y sub c. And the moment now in here will be equal to f r net times the distance y. So what we can do in here is we can equate this equation to this equation. So first we can find the moment by using this equation, and when we find m, the moment about O, we can plug it in here, and when we found the magnitude, we can solve for the distance y. So now let's find the magnitude of the F resultant net. So the resultant force because of air is what? Is pressure of the air times area. Now the pressure of the air is given to us as 200,000 Pascal times the area. The air acts on on the entire cap, so it will be pi over 4 times 2 meters squared. So the area here will be pi. So here we can say that the resultant force due to air is this value, which is 628,318.53 Newton. Now, the force due to the liquid, we will use the hydrostatic force equation on a plane surface, which will be the specific weight times h sub c. H sub c is the distance from the liquid surface all the way to the centroid times area. So the question is, what is specific weight? We don't know the type of fluid to look it up on the water property. So what we will do is we will utilize this information that we're given, which is specific gravity equal 1.6. Now, specific gravity is what? Specific gravity is a ratio between the density of the liquid divided by the density of water. Now, the density of water is something that we can easily find from from any table, which is 1,000 or yes, correct, 1,000 kilogram per meter cube. And the specific gravity is 1.6. So we can find the density of the liquid that we are dealing with. And we know that the specific weight is what? Is density of the liquid times gravitational force. So what we will do in here, we will solve for the density of the liquid. And when we solve this, we will plug it in our specific weight equation or expression. And that's exactly what we did in here. So now the density of the liquid is the specific gravity times the density of water times gravity, h sub c times area. Now h sub c, we found it to be this expression, and the area is pi r squared divided by 2. This is the area for a semicircle. Now we plug in the values that we found and the values that were given. And this will give us that the resultant force due to the liquid is what? 10,464 Newton. So we said that F R net is what? Is adding these two values, and that's what we did in here. So this will be 638,782.53 Newton. Now let's use the moments to find the Y value. So the moment in here, so we will say that the moment of air times the radius, and the moment of F liquid will be 1 minus Y sub C, and that's what we have in here. We plug in the values that we have, and it will give us that the moment is what? 634,341.47 Newton times meter. So now let's use this value in here and equal it to the FR net that we found to solve for Y. So now we can solve for Y by taking this to the other side of the equation from multiplication to division, and it will give us that Y is 0.99 meter. So it's very close to the center of the cap. The resultant net force due to the air and the liquid acts 0.99 from the bottom of the, so because from the bottom to the center is 1 meter. This result force net acts 0.99. So you can say it acts on the same point. All right. Next problem and last problem. 2.57. In here we are told that we have forms. You know, in structure in contractors, they use forms, and they put inside these forms, these wooden forms usually, concrete to give, to shape the concrete the way they want. Forms used to make a concrete basement wall, each 4 feet long. Form is held together by 4 ties, 2 at the top and 2 at the bottom as indicated. So here you have 10 feet, and if you think about it to you or into the page, we have a 4 feet width of this form. On the other side you have another tie. We are asked here what? We are asked to determine the tension in the upper and lower ties. So we want to know how much tension in these ties, or in other words, how much force these ties are applying. Assume concrete act as a fluid with a weight of 150 pound force over feet cube. So let's take a look at one side of these forms and see what are the forces that's acting on it. That will help us find the tensions. So this is our form in here. Right here, we're going to have our force, or in other words, the tension, the top, and this is the force at the bottom. Now, we told in this problem that we will assume that this concrete have a fluid weight or a specific weight. And in hydrostatic force, we want to find the centroid, correct? So here the centroid is what? Y sub C is H sub 2. H is in here is 10 feet. So that's where C will act. So that will be 5 feet up, 5 feet down. All right. And the force that, which is the hydrostatic force on a plane surface in here, will act at the center of the pressure, which is usually a little bit below the centroid. So that will be the resultant net force. And this will be the location of the resultant net force from the liquid surface. And here we will take the moment at the bottom. You can take also the moment at the top. So now let's find the hydrostatic force. Now, this is our hydrostatic problem. Now we know it. Now the specific weight, it's given to us. The H sub C, which is the distance from the liquid surface to the centroid, which is 5 feet. And the area in here, area is base times height, which is 10 times 4. So the resultant net force due to the weight fluid is 30,000 pound force. Now we want to use this equation. We use it to locate the hydrostatic force. So here Y sub C is the distance from the water surface to the centroid. So that's 5. The area, we said 10 times 4, which is 40. Now we need to find the area moment of inertia, where the axis of rotation acts at the center. So it will be this equation, which is base times height cube over 12. The base is 4, the height is 10 cubed divided by 12. It will give you 333.33 feet to the power 4. Now let's plug in the values that we found. So this Y sub R will be 6.66 feet. So we found the Y sub R, we found F sub R. So now what we need to find is the force on the top and the force on the bottom due to the ties. And that's by using, summing the moments equal to 0 and summing the forces using the 3 static equations. So first thing, we sum the forces in the x direction equal to 0. So F sub R go to the right, positive, and the top force and the bottom force going to the left, negative, negative. The sum of the moment equal to 0. So in here, so F sub R will rotate, will cause the form to rotate clockwise. So that will be negative times the distance from here to here, which will be 10 minus 6.66, which will be 3.33. And F sub B and F sub T will cause the form to rotate counterclockwise. So this will be F sub T on the top, and the distance from here all the way to axis of rotation, it will be, we will subtract from 5 minus 1, 4. 4 plus 5 is 9, plus F sub B. So F sub B to point O, or the axis of rotation, is 1 feet. So F sub B equal 1 equals 0. So right here we will move F sub R to the other side of the equation. And here what we want to do is we want to solve for either Ft in the beginning or Fb. So what we will do is we will utilize this equation right here where we sum the forces in the x direction equal to 0. Here F sub B, what I will do, I will just move it to the other side of the equation, which is right here, and it will be F sub R minus F sub T. So now let's plug in F sub B into the sum of the moment equal to 0 in here. So it will be 9Ft. Great. Now we substitute F sub B with this expression, which is F sub R minus F sub T equal to 3.33 F sub R. So 9 minus 1, because here Ft and here is Ft, so it will be 8 Ft plus F sub R equal 3.33 F sub R. So F sub R will move to the other side. We will subtract 3.33 minus 1, it will give us 2.33. So now 2.33 F sub R, we found it to be 30,000. That's what we have in here. and we can take 8 from multiplication from one side of the equation to division to the other side of the equation. That's what we have. And F sub T will be what? 8,737.5 pound force. Question. This one, the top, that's the value. The bottom, will it be larger or smaller than this? Now, F sub B will be what? 21,262.5 pound force. Now, how did we find it? Simple. We found F sub T, right? We will go back to this equation, F sub B. F sub R is 30,000 minus 8,737.5. And here we found the top force and the bottom force due to these ties. That's the end of these problems. Thank you very much for watching. Have a good one.